Hey guys, Mr. Santiago here for the last video in our Unit 11 series on kinetics and equilibrium. So last video we talked about Lechat's principle, and we should, hopefully by now you have a good feeling for equilibrium and how reactions will shift left or right and head towards equilibrium, because remember, all reactions always head towards equilibrium. But now we're going to go ahead and start solving some problems using the equilibrium expression that I introduced in the last video. And so we have a few different types of problems. We're going to talk about these different types, and we just labeled them type 1, type 2, type 3, type 4, just to kind of keep it organized. So let's go ahead and take a look at the first type. We're going to solve for one equilibrium concentration, or we can solve for the constant K, equilibrium constant K, given all concentrations at equilibrium. So here are the steps. Number 1, write a balanced equation. Easy enough by now, hopefully for you guys. Number 2, write the equilibrium expression. You guys should have had enough practice with this. So again, this is just products over reactants, right? Use the coefficients as your exponents. Number 3, plug the values into the expression, and then just use your calculator and solve the problem. All right, so let's go ahead and take a look at what that looks like with sample problem 8. All right, so here's an equation they gave to us. It's already balanced for us, so that's nice. Now, at equilibrium, a 500 milliliter flask contains 4 moles of bromine, 2 moles of chlorine. If the equilibrium constant K for the reaction is 11, it's equal to 11, what is the concentration of bromine dichloride? All right, so in this particular case, let's go back to the steps. We want to write the balanced equation. That's done for us. We want to write the equilibrium expression. Okay, so we have to write that, but then also take a look at number 3. We want to plug the values into the expression. Okay, so what I'm going to do is I'm going to just pause the video, see if you can work this out. If not, just follow along with me. But if you think you got it, just go ahead and either way, come back to the video and we'll take a look. I'm going to go ahead and show you the answer for this, and I'll explain how we got through to the answer. So let's go ahead. The balanced equation is already here. So let's go ahead and take a look at the K expression down here. Right, here's our K expression, products over reactants. So here are the products over here. We have a 2 as a coefficient for the chlorine. So therefore, we need to make sure that that's squared in the equation. And then the 2 over here as a coefficient for the bromine dichloride as a reactant. We have to make sure that that's squared over here as well. So once we have this, theoretically, you can think maybe we can just plug in the numbers. They gave us our K value. So let me change the color here. All right, so they gave us our K value, which is 11. So that just gets plugged in for K. No big deal there. We have these values here, but you might be wondering, where did these values come from? I don't see those values up here in the question. Well, the reason why these numbers are here is simply because, remember, these brackets represent concentration, and therefore we have to use concentration values when we plug them in. Well, in the question, we weren't given values in terms of concentration. They told us how many moles of each we were given, and they told us the volume of the container, but that was it. So we actually have to do an extra step and calculate the concentration for each of those. So each of these substances here. So for the bromine, the concentration of bromine is going to be the 4 moles in your half liter. So 500 mils, right? Move the decimal 3 places. That gives you 0.5 liters. So our 4 moles divided by 0.5 liters, and I guess this should be 4.00 to match sig figs here. So there's a mistake there. But in any case, 4 divided by 0.5 is going to equal 8. So we have 8 moles per liter of diatomic bromine. That's the concentration. And then here we have 2 divided by half liter, which is going to give us 4. So there are the actual concentration values for your starting, your reactants here. So we're going to plug those in where they belong, right, in place of here. Square the chlorine, which is equal to 4 moles per liter, and we're going to solve for the bromine dichloride, the concentration of bromine dichloride, which we can just call X. All right, so, and of course it's X squared, right, because of this right here. Right, so we're solving for the concentration of bromine dichloride, but it's squared, so therefore it's going to be X squared. So what do we do here? Well, we just mathematically solve for X. So we can rearrange this to get X by itself. So we have X squared equals 128 over 11. So when you do the math, right, this is what it works out to. And to solve for X, right, Just go ahead and take the, do the math, take the square root of both sides, and then you get your final answer, okay? And so it would be 3.41 moles per liter of bromine dichloride. Okay, so really it's just kind of a plug and play. The only exception is you got to kind of do a little extra step here and calculate the concentration values because they didn't give us any values in terms of concentration. Okay, let's move on to problem type number 2. If you're given the initial concentrations and one equilibrium concentration, find all of the equilibrium concentrations. All right, so here are the steps for working something like this out. Number 1, you want to write the balanced equation. Again, easy enough. Write the equilibrium expression. By now that should be pretty easy. Number 3, you're going to set up a reaction table. We also call this an I.C.E table. I.C.E, I for initial, C for change. So the initial concentration, the change in concentration, and then E for the equilibrium concentration. All right, now I'll show you what that looks like in a moment. You're going to set up a reaction table to calculate the equilibrium concentrations. Now you're basically just going to plug in the table with the values that you're given and then solve for the rest. And then you're going to use the chemical equation to kind of help you do that. And I'll show you what that means when we get to that point. All right, so let's go ahead and take a look at what we can use this method to solve for. Here's a reaction here. All right, so we have sulfur trioxide decomposing into sulfur dioxide and oxygen gas. We're given 2.5 moles of sulfur trioxide placed in a 1 liter flask. Now the nice thing about this being a 1 liter flask is when you do the math, 2.5 divided by 1, right? Basically, so you can just assume this. You can just assume this is concentration, right? Moles per liter because it's a 1 liter flask. Okay, and then it's found that that 25% of the sulfur trioxide has reacted. All right, so let's go ahead and plug in what we can on this table. Now here's the I.C.E table. We're going to set it up as a grid, just like this, with your initial, change, equilibrium. So I, C, and E. This column, right, represents what's going on with sulfur trioxide. This column represents everything going on with sulfur dioxide, and this column represents what's going on with oxygen. So initially, they're placing 2.5 moles per liter in the flask. So the initial concentration of the sulfur trioxide is going to be 2.5. Okay? Now, at this point, that's all they really gave us. The only other information they gave us was at equilibrium, it's found that 25% of the sulfur trioxide has reacted. Well, think about this. If 25% reacts, that means you have 75% remaining at equilibrium. All right, so if you have 75% remaining at equilibrium, well, 75% of 2.5. So let's go ahead and zip down to the full table and I'll explain how we filled everything else in. So here's your original 2.5 moles per liter. If you take your 0.75 times your 2.5 moles per liter, that's going to give you 1.88 moles per liter. That's your 75% that's remaining at equilibrium. So we're going to plug that in to the equilibrium box here, 1.88 moles per liter. Now, if you started with 2.5 moles per liter and you end up with 1.88, well, then what happened? Well, you lost 0.62, right? You went down by 0.62. So the negative sign here is representing the fact that this is getting used up, right? You're losing, this concentration is going down from the initial value. So that's where the 0.62 comes in. So 2.5 minus 1.88 equals 0.62. Okay, so that's your change. Now, once you know the change for one of these, any one of them, well, now we know the change for all of them, simply because you have a 2 to 2 to 1 ratio here, right? Look at your coefficients, 2 to 2 to 1 ratio. So this is a 2, that's a 2, so a 2 to 2 ratio is the same as a 1 to 1. We're going to give this change a positive 0.62 simply because you're creating the product. So at the beginning, right, we originally only placed the sulfur trioxide in the flask. There's nothing else that was placed in the flask. Therefore, your starting amounts for the other two, the products, are 0 because none of these, we didn't start with any of these guys initially. So knowing the change, which is 0.62, 0 plus 0.62 would give you 0.62 moles per liter of sulfur dioxide at equilibrium. Now for the last part, oxygen, notice this is a 2 to 1 ratio. So since this is 0.62 moles per liter, this is going to be half that, 0.31 moles per liter, because it's a 1 to 2 ratio here, right? So there's your 1 to 2 ratio. So 0 plus 0.31 equals 0.31 moles per liter. So that's how you would fill this out. So the question is asking, find the equilibrium concentrations and the equilibrium constant. So we just found the equilibrium concentrations here. That's done. That part is answered. The part that we have left is to find the equilibrium constant. That's your K value. So for K, again, products over reactants. Here are your products, the sulfur dioxide and oxygen. And remember, K is always used at equilibrium. So we must use the data right here in the equilibrium section of the table, of this ICE table. All right, so we're going to have 0.62 squared because you have the coefficient of 2, so that's 0.62 squared, right? There's your concentration of sulfur dioxide. And then we have that times your concentration of O2, right? And that's a coefficient of 1, so there's just an invisible 1 here. So there's 0.31. That's what we're putting up here. Down here we have our reactant concentration at equilibrium. So that's your 1.88, right? And that's going to be squared because of this coefficient of 2, right? So we have to make sure that you square that. Now you just plug everything in the calculator and you get your answer. Again, K doesn't have units, so we don't need to worry about that. So that's it. That's all. We're done. We got our equilibrium concentrations by filling out our ICE table, plugged everything in, and found K. All right. Type 3, problem type 3. If you're given an initial concentration and the Kc value, find the equilibrium concentrations. Okay, so in this particular case, same first two steps, write the balanced equation, write the equilibrium expression, even part 3, set up a reaction table. Now, this is where things change a little bit. Because you're only given the initial concentration and you're not given any other information about what happens or how it got to equilibrium and what the equilibrium value is, we have to use, mathematically, algebraically, we have to use x as a placeholder. So we're going to use x and solve for x in this case when we fill out our ICE table. And you'll see what that looks like when we do the next sample problem. So let's take a look at that. Number 10. Here's our balanced chemical equation. They're also giving us the value of K, which is 1.2. Now, if you place 0.5 moles of nitrogen monoxide in a 750 milliliter flask, what would be the equilibrium concentrations of all species? So they want to know what these guys are. They want to know what the equilibrium concentrations are of all of these guys. So if you're going to place 0.5 moles, and that 0.5 moles is in a 750 ml flask, well, that's 0.75 liters. To find the concentration of nitrogen monoxide, right, you have to divide moles per liter. So 0.5 divided by 0.75, well, that would be 2/3, right? So that would look like will be point in repeating sixes, right? But we'll just keep it to 3 sig figs since that's what they're giving us here. All right, so we'll do that. That's kind of what the calculator would show you if you were rounding to 3 sig figs. Okay, so here we have the initial value, but that's really all they're giving us. And the only other values we know are the initial values of these because we don't have any of them, right? None of that was put in the flask. So we have 0 product at this point. So those are the only values we have to put on the table. So we have to use x as a placeholder. We want to know what is the change in x. Therefore, if you know what the change is, then you can do the math and find out what the equilibrium value is. So we're going to use x as a placeholder. Now, since this is a 2 to 1 to 1 ratio, look at the coefficients. It's a 2 to 1 to 1 ratio. This is going to be minus 2x. All right, hopefully that makes sense because it's going to be a 2 to 1 to 1 ratio. And the negative sign is because, again, you're using this up. This has to go down. This is all you have in the flask. So the only direction that this reaction can proceed is to the right. So therefore, this is going to get used up right away as soon as the reaction starts. So we're going to go down by X amount, all right? And it's going to be 2 times that because that's the ratio here. All right, now, knowing that this is a 2 to 1 to 1 ratio, that means that this is going to be increasing, right? I'll put a positive sign here, by X number of moles per liter. And then the same over here, right? So both your products would be increasing by X number of moles per liter. Now 0 plus X, well, what's that? Well, that's just x, right? 0 plus x, that's just x. And then this right here would be, well, I mean, there's no way you can kind of work with this, so we're just going to have to, for the most part, rewrite this as 0.667 minus 2x. All right, so that's how you would fill out your ICE table for a problem like this. Now, how are we possibly going to solve when you have x's everywhere? Well, the reason why we are able to solve is simply because they gave us the k value. And that's the only way we'd be able to solve is if they give us the k value in this type of situation. So because we're given k, well, now we have enough information to solve. So I'm going to skip down to the answer key to make it a little quicker and easier for us to go through this without you having to wait for me to write everything out. Okay, so this is just exactly what we just wrote in the other. Just ignore the answers for now, right? I'm going to show you the math and how we got to the answers, but this is essentially what we started with on our previous slide. Okay. Now our K expression, if you write it out correctly, products over reactants is going to look like this. Okay. Now all we're going to do is we're going to plug in the numbers. Just again, K represents equilibrium, so we only are looking at the equilibrium row right here, equilibrium row, and we're going to plug those numbers in. So in place of for the concentration of diatomic nitrogen, which is over here, we're going to look at that. That was what we labeled as X. So we're going to put that up here. That's going to plug into here. And then, so in other words, let me just draw this out. So X is going to go right there for nitrogen. This X is going to go right over here for oxygen. And then for the nitrogen monoxide, right, you have this. That whole thing needs to go right in there for the nitrogen monoxide, okay? So that's essentially how we're plugging it in, and this is the end result. Now, we're also plugging in K, right? They gave us our K, so we're plugging that in as 1.2. So once you have that all set up, well, now we actually have enough information to solve. So since since both of these are squared, well, take the square root of both sides. And if we take the square root of both sides, what happens? This square goes away, that square goes away. Okay, and you're basically going to have the square root of 1.2, right, times this whole thing here. And that's how we continued on with the math. So if you take the square root of this times your 0.667, you're going to get this, 0.73066. If you take your square root of 1.2 times negative 2x, you're going to get negative 2.19089x. And I'm just extending out the decimal values. We'll adjust for sig figs later, but I don't want to cut it short just yet. We want to adjust at the end. And then, of course, x is by itself right here, so that's all equal to x. So once you do that, you can take this value, bring it to the other side by adding, plus 2.19089 to the other side, and that's going to give you this. Then we need to get x by itself by dividing both sides by 3.19089, and that'll give us the answer here. Now, we solved for x. We solved for this, and we solved for this. So let me get rid of some of this, get this out of the way so we can see a little better. All right, so we solved for this. We solved for x. So the concentration of oxygen, right, is 0.299 moles per liter. The concentration for nitrogen is x, so it's 0.229, excuse me. Now this, we have one last step, because this right here, that wouldn't be the concentration for nitrogen monoxide, simply because you have to plug in your x value into the x, into this formula right here. You have to actually plug that in to solve. So that's what we did down here. So for the chemical equilibrium concentration for nitrogen monoxide, we're going to have 0.667 minus 2 times 0.229, and that will give us the concentration for nitrogen monoxide. And this the EQ, don't worry about that. Don't let that worry you wondering what that is. That's just your nitrogen monoxide concentration at equilibrium, because we had the initial, that's the little I here, we had the initial nitrogen monoxide concentration that we had to put in initially, and then we have the concentration at equilibrium. So that's what the I represents, that's what the EQ represents. Okay, so there's how you would solve for all three of those. So that's one last step you have to remember. You have to plug in X, the number that you get, plug it in, right, and then go ahead and do the math to actually get your value. And that's how we would solve for this. So everything's solved. All right, so that's number 10. Let's take a look at number 11. Now, for number 11, here is the chemical equation. They just gave you a basic template of a chemical equation. A plus B yields C. They gave us the Kc value, again, 1.2. Now they're asking us here, if you place 0.5 moles per liter of A, zero point 0.5 moles per liter of B in a container, what would be the equilibrium concentrations? So in this particular case, we're starting with equal amounts of A and B. So you're going to have your 0.5 molar over here. You're going to have your 0.5 molar over here. And then C, they're not adding any C to this, so we know that's going to be 0. Okay, so I'm not going to write this out because I'll show you the answer on the next slide, with everything filled in. Okay, so once you have your 0.5 here and 0.5 here, you're going to do kind of a similar thing. We have to use X as a placeholder. So we're going to have minus X. Now this is all a 1-to-1-to-1 ratio here, right? So we're going to have minus X over here, and then you're going to have your plus X over here. So 0 plus X would be X. And this would be 0.5 minus X, 0.5 minus X. So let's take a look at what that looks like. Again, ignore the answers, right? I'll show you how we got to those answers. So here's your 0.5 minus X, 0.5 minus X. That's what we started with. And then your equilibrium, we're going to represent it as 0.5 minus X for both of these. And then, of course, 0 plus X is X. So for the K expression, again, products over reactants, here's your K expression. That's your K. We just plugged it right in, 1.2. Your product, there's only one product, C, and that's X. So that's where X comes from here. Then you have your reactants, right? This times this, so 0.5 minus X times 0.5 minus X, wasn't that the same thing as 0.5 minus X squared? Yeah, it's basically the same thing. Unfortunately, in this particular situation, we don't have the luxury of just taking the square root of both sides to get rid of the square because this is not squared. This is by itself, so that's not going to help anything. So unfortunately, we have to actually multiply this all out. We have to actually do the math here, 0.5 minus X times itself. And that's what this represents here, the X squared minus X plus 2.50. So if you take this and you multiply it by itself, you're going to get X squared minus X plus 2.50. So then we cross multiply with 1.2, and that's how we're getting to this. So this equals X. So you have your original K value times your reactant totals here equals X. Now, because of all of this, because that square kind of messes things up and makes things a little bit more difficult for us. So unfortunately, we're going to have to use the quadratic formula to solve for this. So when we use the quadratic formula, if you remember, you have to set everything equal to 0. So we need to still multiply this out, right? Let's just go through and multiply this all out and then get X equal to 0. So that's what we did here. We multiplied it out, and it was still set equal to X. So now by setting it equal to 0, right, we just bring the X to the other side, you get this result. Now we have our setup where we can use the quadratic formula. So this would represent your A, right, over here. This represents your B, and this represents your C. This would be your C in the formula. Okay, so let's take a look at the quadratic formula. So this is kind of how it's all set up. Remember, it's X equals negative B plus or minus, right, and then the rest of this stuff. So we have to actually do this twice. We have to do it using the plus sign, and then we'll have to do it again, same equation, but using the minus sign. And then we'll just see which answer makes sense. So plugging in all the numbers, right, again, this is your A, this is your B, and this is your C, right? Okay, so A is 1.2, B is 2.2, or negative 2.2, and C is 0.3. Okay, so after plugging all of these in, okay, you're going to get an answer using the plus sign. You're going to get an answer of 1.68. Now that does not make any sense. Now why doesn't it make sense? Because, well, how could your equilibrium concentration be 1.68 when your starting concentration was 0.5? How could you have more than what you started with? Because when you first put these in, we know the reaction has to go to the right. It has no choice. We don't have any, even though it's a reversible reaction, there's no product when you first start the reaction. So there's no way that C can decompose into AB if there's none of it to start with. So therefore, the reaction we know has to go to the right to begin with, which means you're going to use up A and B, which means it has to go down. Your concentration values have to get lower. So your equilibrium concentration needs to be lower than what you started with. And that does not make any sense because of it. Okay, so then when we use the negative sign here in our quadratic formula, we get an answer of 0.148 moles per liter. That makes more sense, right? That makes more sense. So our concentration of C, right, is just directly 0.148. Our concentration values, equilibrium concentration values for A and B are going to be calculated simply by plugging this into X, like we did in the last problem. And we're going to do that for both of these. You got to plug it in here and here, but it's the same numbers. So your answer for this is going to equal your answer for this. So when you take 0.5 minus 0.148, you're going to get 0.352 moles per liter, and that would be the same for A. Okay, and so those would be the equilibrium concentration values for this type of situation. Okay, moving on. Problem type 4. This is actually, I think, one of the easier types of problems. In any case, what we're going to do is, so if you're given, or what you want to do is you want to determine whether or not a mixture is at equilibrium. So the question is going to ask, is this at equilibrium? Is this system at equilibrium? Or if not, then which way does the reaction need to proceed to establish equilibrium? That's essentially what type of question you're going to get when you need, when you have a problem type 4. So number 1, write the balance equation. Same thing, right? Number 2, write the equilibrium expression. Same thing as before. Number 3, plug the values into the expression and solve for Q. So now, since remember, we only use K when we know we are at equilibrium. Well, if the question is asking if we're at equilibrium, well, then we don't know. We don't know if we're at equilibrium. So we can't use K in this case. We have to use Q. Okay? So we're going to use Q, and then we're going to compare it to a known value of K. So they actually have to give us a known value of K in a problem like this. So we're going to compare. We're going to say, okay, if Q equals K, then we know the reaction is at equilibrium. If Q is greater than K, then we have too many products, so the reaction must shift left. If Q is less than K, there are too many reactants, and the reaction must shift right. All right, and we'll take a look at how that all comes together in problem 12. So here's our balanced equation. Here's our K value that they gave us. If a reaction mixture contains 0.0025 moles of nitrogen, 0.0025 moles of oxygen, and 0.0035 moles of nitrogen monoxide in a 700 milliliter flask, is the reaction at equilibrium? And if not, which direction must it proceed to reach equilibrium, and explain your reasoning? Okay, as always, pause the video if you think you can do this on your own, give it a shot at least, and then come back to us. All right, so number 1, we know that we're dealing with concentration values. So since we have a 700 milliliter flask, we have to convert all of these guys to concentration values. So we have to divide 0.0025 by 0.7 liters, right, to get our concentration, and then do the same for these guys, divide by 0.7. And so that's what we did over here, okay? So we divided everything to get our concentration values. Then we're just going to set everything up like we normally do. But again, we're not using K because we don't know if it's at equilibrium or not. So we can't use K. So we're going to use Q. But you set up the same way, products over reactants. Now, since we have a square here for nitrogen monoxide on the reactant side, we have a square here, okay? So since there, well, it's not a square, it's 2 as a coefficient. Since we have 2 as a coefficient, we square here. Now, here we have a square, even though there's no coefficient of 2 over here, but the reason why it's squared is because these two values are the same. In other words, you have 0.0025 moles per liter, 0.0025 moles per liter, okay? Actually, let me back up. Products, excuse me. Yeah, your products, your nitrogen and your oxygen are your products. So we have 0.0025, 0.0025, but when we did the math, we got these answers right here. So here's what we got there. All right, so that's where your 0.0036 came from. So excuse me, I was looking at these numbers rather than the numbers we should have been looking at. In any case, so that's where your 0.0036 comes from, and since they're both the same value, this times this is just, this times itself or squared. So that's where the square came from here, not from one of the coefficients, but because these two values are the same. In any case, this is your setup. Plug it into the calculator, get your answer. Here is your answer for Q, all right? But that's not what they're asking for in the question. What they're asking for in the question is whether or not we are at equilibrium. So you have to compare Q with the known value of K, which they gave us up here. Now, look at the difference. Q is greater than K, right? So think about that for a moment. Q is greater than K. Now remember, all reactions head towards equilibrium. They always head towards equilibrium. So that means that this number needs to go down, 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 down until it reaches this value. The reaction is going to proceed until this value reaches this value. So it's going to keep on going down. Well, how would this go down? The only way to make this number smaller is to make the denominator bigger while the numerator gets smaller. So if the numerator is getting smaller while the denominator is getting bigger, that is going to cause this to go down, 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 down. So what direction is the reaction going to be heading in to make this happen? Well, if your numerator needs to go down, your numerator represents your products. So these are your products. If they need to go down, that means they need to get used up while you're making the denominator bigger, which are your reactants. If your reactants are getting bigger, it means you're producing reactants, which means the reaction must be going this way to reach equilibrium. Okay, so there are too many products, not enough reactants. Therefore, the reaction will proceed to the left, all right, in order for your Q to become equal to K. Okay, so that's basically all there is to that. So the math isn't very difficult. Make sure you're using values of concentration, plug it in to solve for Q, your reaction quotient Q, plug it in, solve it, and then compare those two values, right? And that should tell you which way the reaction needs to go. Does your Q need to get bigger? If so, the reaction goes to the right. If Q needs to get smaller, say reach K, then your reaction goes to the left. In this case, Q needs to get smaller, so the reaction proceeds left. Okay, and that's really it, guys. That's the end of the slideshow. We're done with Unit 11, and so hopefully, you've made sense of all of this, and especially for you guys wanting to take AP Chemistry next year, this is going to be an important, very important part of AP Chemistry next year. So you want to make sure that you have a good grip on all of this. Okay. In any case, till next time, have a good day.